So can everyone hear me? Yeah? Okay, so thanks for coming to the talk. Today I'm going to talk about private communication with state-based rate limiting. So basically what we want to do here is we want to have like networking that's private but is also DOS resistant. So let me sort of get into it and I'll explain where it starts to get difficult. So when we use blockchain or when we use computers in general, we have to communicate between different computers. This is like a challenging problem because we want to make these networks peer-to-peer so that there's no like central party, so two people can communicate without having to go through some kind of central intermediary. But this makes the kind of network providers very powerful. And when you use a peer-to-peer network, it becomes easy to kind of censor a single, to censor like transactions or communications. It's also possible to track users, and if you track users, it makes it easier to censor those users. So these are kind of problems that are inherent to the kind of networking stack. They're things that we need to be careful about when we're kind of designing new systems or comparing older systems. So let's take an example of a private peer-to-peer network and kind of see how it works and what some of the drawbacks are. So one example is Tor. Who here has used Tor before? Oh, cool, okay. Yeah, so Tor is basically like a private network where your traffic gets kind of shuffled and hidden as it passes through the network. So Tor is like permissionless, it's free to use, anyone can set up a Tor node and advertise it and people can use it. But there's some major problems with Tor. For example, if you use Tor a lot, you've probably seen this second screen here, where you want to go to a website and then they say, oh, you can't go to the website, you have to put in this CAPTCHA. And the reason for this is that because anyone can join Tor and anyone can use Tor, Tor has become like kind of abused because people use it to, for example, set up millions and millions of Gmail addresses or upload lots and lots of videos to YouTube. And for that reason, Tor is very slow, and it's really very annoying to have to deal with this kind of CAPTCHAs all the time, to the point where people don't really use Tor, or it just hurts. So one idea is that, okay, why can't we use Tor with Ethereum today to give like node privacy to the accounts? So one of the reasons here is that in the current situation, if you receive a transaction, if you see like invalid information, or if you're the victim of a DOS attack, you know exactly who's doing it. Because every time you receive a message, you know where it came from. And if that person is kind of abusing the system or trying to send you too many transactions or selling you invalid transactions, you can simply ignore them. You can simply stop responding to their requests and refuse to send them any information. But that's not the case with this kind of private, right? Because when you receive a message, you don't know where it came from. Yeah, you know which person it came from, but you don't know which node it came from in the network. And because of that, it becomes difficult to kind of have rate limiting, to say, oh, I only want to receive one message per second per user. So this starts to be a problem if you want to apply private communications to like blockchains in general. So some of the goals of what we're trying to, what we want to make in this talk, or where we want to get to, is we want to have a private peer-to-peer network, but we also want to have this like strong rate limiting. So if there's DOS attacks or spam attacks, we're kind of a little bit more resistant to that. Okay, so let's look at like an example that already exists. So one example of a DOS-resistant privacy mechanism is Whisper. So basically how Whisper works is that every time you create a message, you create like a proof of work. And you provide that proof of work with your message. And when I receive your message, I first validate the proof of work. If the proof of work is invalid, I ignore your message. If the proof of work is valid, I accept your message as being real. So then we have this kind of rate limiting applied. We have this kind of limit on the number of messages we can receive per second because we have limited computational power. That we have this proof of work that's difficult, so we have a limited number of messages that we can receive. So like one kind of weird example of how this could be used in real life is that if you have a lot of people who want to talk to you all the time, you could insist that people only spoke to you in haiku. Yeah, that everything someone says has to be a haiku, and that's like this kind of difficult thing, right? And you would presumably receive less communications because you put this limit on people. But people at least have to spend the time to turn everything that they're saying into a haiku. But there's a problem in both of these systems. For example, if you put this like haiku limit on people, they could be just good at making haikus. And people who are good at making haikus could like speak to you a lot more than people who weren't. And similarly, this works with the like computational proof of work, right? Because if I want to send something with my mobile phone, I have very limited computational power. And this computational power can be like beat, I can get a similar computational power with my laptop, or with AWS, I can pay and have like a huge computational power. So this is kind of the problem with Whisper, and in general the problem with proof of work. So, okay, so then the naive thing to say is that, okay, so we know that proof of work will work, so let's try and do proof of stake, because we can come up with this mechanism where, what do we do? So we make a smart contract and we say, okay, everyone who wants to send messages has to put some deposit into the smart contract. Yeah, and we have a list of all the people who are allowed to send messages. Every time someone sends a message, they sign that message and they send it to one person. And if I receive two messages from the same person in the same epoch, so every time someone sends a message, they say this is for epoch number 1, and then they have the hash of the message that they're sending, and they sign that. And if I receive a message, if I receive two different messages from a single user in the same epoch, I can slash them. I can remove their deposit. So basically, what happens is if you send too many messages, you get slashed. You lose your deposit, right? But the problem here is that this breaks privacy, right? Because we have this way to slash people, I know every message that people send, and I can link every message that someone sends together. So we just completely lose our privacy. But we have this kind of strong sort of rate limiting, and we also have these guarantees that if someone abuses the system, we can kind of harm them in some way. We can kind of attack them. Okay? So let's try and add privacy to this proof of stake-based system that we had before. So basically, what we do to add privacy is we use something like we use a zero-knowledge proof. So basically, a zero-knowledge proof is a way to prove that you did a certain operation or hold a certain credential without revealing what that credential is. So basically, what we do is we do the same thing again. We have a smart contract where people deposit money. And when they deposit money, instead of defining a public key that they're going to use to sign their transactions, they define like a semaphore public key. That's a special public key that works inside our zero-knowledge proof. So basically, we make this group of semaphore people, and we do the same thing again. Inside the zero-knowledge proof, we sign the messages. So for every epoch, which we define as this external nullifier, users can define a message, a signal, and they put these two things as an input to a snark, and inside the snark they prove that they know a public key that is in the Merkle tree, and then they prove that that's in that Merkle root, and then we reveal the Merkle root and something called a nullifier. So in this case, the nullifier is like the hash of the private key and the external nullifier. So let me do an example. So this is kind of like the hardest few slides of the talk, and it'll get a little bit easier in a few minutes. So let's just do an example of what's happening here. Okay, so we have our group here where everyone comes and joins. We have A, B, C, D. These are unique users who have joined our group. And each user can create a zero-knowledge proof. And this zero-knowledge proof will reveal 4 pieces of information. Yeah, the external nullifier, the signal, the Merkle root, and hash. Okay, so let's see here for 2 epochs. Okay, so each epoch we change the external nullifier from So the first epoch has 3 messages. The second epoch has 2 messages, has just a single message. Okay, so here are the messages that the user sent. We don't know which user sent these messages, but we don't know which user sent these messages, but we have a strong guarantee that one of the people in our group sent these messages. So the first message is hello. So someone said hello. They calculate the Merkle root, which happens to be the Merkle root of this group, and they reveal their external nullifier. So the external nullifier is like unique to every user per signal. Yeah, so every epoch, everyone gets a new external nullifier, but during an epoch, you can only reveal your external nullifier. You can't reveal another external nullifier. Okay, so it's like a receipt or a unique ID that changes over time. That's probably a better explanation. So we have this unique ID that changes over time. So if you look at the external nullifiers, we see that there's 4 external nullifiers, but we have 2 external nullifiers that are the same. So what do we know based on these 2 nullifiers being the same? Yes, exactly. So they're coming from the same user, right? Because we have these nullifiers that are unique per epoch, we know that some user has broken our guarantees here. Yeah, someone is double sending a message. Okay, this is kind of what we want to do, and this is what we were doing with the previous mechanism. Yeah, well, instead of using signatures before, now we use these kind of these nullifiers to reveal it. Yeah, and our zero knowledge proof is there to sort of hide our inputs and to make sure that people can't cheat. That people can't say, oh, this is my external nullifier, when it's not. Okay, people are bound to their external nullifier, they can't change it. Okay, cool. Okay, that was like mostly the hardest part of the talk. There's another like less hard part coming up. That was the major thing to understand. So if people have trouble with it, we can have questions at the end, or we can talk more later. Okay, but let's keep going. Okay, so if you didn't understand it completely exactly what was going on in the previous slide, just you can model it as saying that, okay, we have this way of proving that you're in a group without revealing who you are, and we have this like updatable thing that limits people from, we have this updatable nullifier, that every time we enter a new epoch, we have a new nullifier. So the epoch is like 1 second. Every second, people are allowed to send another message. Okay? So let's talk about some of the limitations of what we've had before. So all messages are linked together. So each message in an epoch is linked together, but that's kind of okay. That's exactly what we're sort of looking for here. And another problem is that, let's say that there's more than just me receiving messages. Okay, if it's just me receiving messages, this works totally fine. I can receive messages, and I know when someone's sending 2 messages, so I can ignore that. But if there's 2 people, then the overhead gets much more. Because every time I receive a proof, I have to share it with the other person. Yeah, because they need to make sure that I hadn't received one of the messages that they did. So this is to prevent like double signaling between 2 different parties. So this adds like a lot of overhead to the network, right? Because we have a lot of extra communication that we need to do, and this doesn't really scale very well when we have more and more nodes. So there's a lot of overhead to do this. Another problem is that there's no punishment for a DOS attack. Okay, someone can do a DOS attack, and I can just ignore them, but I can't harm them. Yeah, I can't say, okay, you have to stop. There's no way for me to do that. No. Yeah, so then we have a bunch of overhead, which I already said, and we know when to punish people. Okay, cool. Oops. Let's go again. All right. Okay, so what we want to do is we want to have this idea of slashing. So we want to have this group where people can send messages, but if people are sending too many messages, we want to be able to say, stop. We want to kick them out of the group, we want to punish them somehow. Okay? So how do we do this? So the way we do this is we need to reveal their private key. So what we do is that when we have our snark, we reveal their private key, we reveal a piece of their private key. Yeah, and we randomly select the piece that we reveal in such a way that if someone sends 2 messages, we reveal the whole private key. And if someone sends only 1 message, we receive nothing. We reveal nothing. We don't reveal any information about what they're doing. Okay? So then it becomes like, if I have 2 messages, I have enough to construct someone's private key, then I can go to the smart contract and slash them. Yeah, I can punish them. So the guarantees of the system now become that you're private as long as you don't send more than 2 messages or more than like a number of messages that we can define later. Yeah, then we can go to the smart contract and slash them. Okay? So how do we do this? Well, it turns out that there already exists a really simple and interesting way to reveal a part of a secret in such a way that if I reveal 1 piece, nobody can reconstruct my secret. Hello? Hello? if I reveal it, so it turns out that we have this really cool way to reveal a piece of a secret if we, in such a way that if I reveal one piece, I don't have any information, but if I reveal two pieces, I can totally reconstruct the secret. Yeah? And this is like an interesting tool that we can use here. So how does this work? So basically what we rely upon is that the idea that you can reconstruct a polynomial if you have of degree n, if you have n minus 1 points. If you have n minus 1 points, you can do linear interpolation and recalculate the whole polynomial. So what we do is we encode the secret as a single coefficient of this polynomial, and then we randomly set numbers for all of the rest. Yeah? And then what we do is we calculate points on this polynomial and we give them to people as shares. And if someone gets two of these polynomials, they're able to if someone gets two of these shares, they're able to reconstruct the polynomial and calculate the secret. And if they get one, there's no way for them to calculate any of it. They have no information about what the secret is. Okay, so this is like some crypto that you can kind of explore a little bit later, but it's just like a component of what we're going to use in order to build a whole system. Okay, so what do we do? So what we do is we construct this Shamir secret share root. So basically, we calculate a bunch of Shamir secret shares, and we put them into a Merkle root. Yeah, and we reveal that Merkle root. We reveal that Merkle root in our zero-knowledge proof. Okay, so now we still don't have enough information to reconstruct the messages. We have a list of the secrets that we have, like a commitment to the secrets that exist, and we don't know what any of those secrets are. So what we do instead. So what we do is that every time someone sends a message, we now send a zero-knowledge proof, but we also reveal one of the secrets. Yeah? So we reveal one secret, and we randomly select the secret that we reveal based upon what the message is. Okay? So each message will reveal a unique secret, and if we have two messages, it will reveal enough secrets to reconstruct the private key. Okay? So let's kind of go through exactly what's happening here. Okay, so we have the same system again. Okay, we have the same, like, here's our nullifier, here's our Merkle root, or here's our external nullifier, here's our Merkle root, here's our nullifier, here's our Shamir secret share, and here's one of our secrets in the secret share. Okay, so if we go through, we see that we have two nullifiers that are the same again. So from before, we know that that means someone has sent two signals. Okay, so now we have a way to punish them. What we do is we check what their secrets they revealed are. So they reveal two unique secrets, and this is enough to reconstruct their private key. From that, we can go into the smart contract and we can stash them and remove them from the root. So now, if someone breaks our rate limiting assumption, we can stash them. Okay? Yeah. So let's just go through exactly what I do when I receive a message from someone. First thing I do is I check that the snark proof is valid. Then I check that we have not received the same message before. Because if we've received the same message twice, it doesn't reveal a separate secret. Then we check the Merkle path of the secret share, and if all of that works out, we accept this as a valid message. We don't have to share this with anyone else. What we can do is we can say, oh, I received this message, and if it's a DOS message, I can stash them in the future. If not, I don't have to store it for a long time. Okay? Okay. Maybe that was a little bit honest. That's right. Let's do this. Okay, so this is my last slide. So conclusions. So we can make like this private peer-to-peer with strong rate limiting. It requires using zero-knowledge proofs. We don't necessarily have to stash every user every time they come up, every time they double send a message, but we can do that if we want. It's still a cost to them probabilistically sending a message that they might get slashed. Also, there's a whole bunch of other privacy stuff that we're interested in making and interested in collaborating with people on. So if people have other ideas about privacy stuff or just want to chat about that, we can talk at the end of the talk. But now I think my time is almost up. I have 20 minutes, right? 10 minutes left. Okay, so I have some extra slides, and I also have like some time to take questions. Okay, so let me go back to my home slides. Okay, so everything works well so far. But one thing that would be nice would be able to receive payments for processing messages. Because if I'm part of the network and I'm sending people's messages for them, I want to be able to receive a payment for this. So basically what we do is that every time someone sends a message, they also say this message was for this person. Yeah, they say, I'm sending a message from me to this person, and they're to be paid for sending this message. And then afterwards what we can do is we can do something called probabilistic payments. So probabilistic payments basically works like this. Instead of me paying you $1, I pay you $100. I give you a lottery ticket for $100 that will win $100 1 in 100 times. And it turns out that these two things are the same. I mean, economically, these two things are the same. The chance of winning $100 is the same as is the same as $1. The chance of winning $100 that pays off 100 times is the same as winning $1, of getting $1. Yeah, so what we do is we use a nullifier as like a source of randomness for this, and we have like an epoch where people commit. So every time I get a message, it's like a probabilistic payment, and then at the end of every epoch, we have this kind of lottery system where we generate some random number, and we say that, okay, we're going to pay people who have X number of nullifiers that are greater than this number, and then we can use that to pay them. I should write this up a little bit later. Yeah. Okay, so I have some time for questions. I actually have a lot of time for questions, but do you have more questions about this? Anyone?
So part of the motivation for moving from proof of work to proof of stake was sort of inequality in access to like computation or hash power. Do you see similar issues with inequality in stake distribution, and would that like have any implications here for like me being able to send messages or not?
Oh yeah, I guess you're right. But this is different because with proof of stake in general, you need to have like, you get more stake proportional to how much stake you have. But in this situation, we could have like, you can put down $1 and join this group, and then you have this kind of strong guarantees about rate limiting, and you also don't need to. Yeah, we don't have to have like, you can send more messages because you have a bigger stake. I guess we will get into problems in the future if we had like huge networks and we wanted to have like a granular limitation to the number of messages people can send. But I guess you could just add more and more leaves to the tree. Yeah. Yep.
Do you see because this relies on syncing a chain, so you need to know about the current state of the chain, you need to know about the who's staked and balance of staked and slashing status and things like that. Do you see any issues with using this for layer one? With the way, like, say you want to privately convey consensus messages, but you need to be synced to convey. Is there any sort of circular issues that arise there?
Well, one thing we could do is we could say that, okay, you can have like DOS attacks in the short term, but in the longer term, you'll get slashed. So we could say that, okay, you can send a lot of messages in this epoch, and we will have like, I'll start to ignore you as soon as you send me 2 messages, I'll reconstruct your private key, and I'll be able to tell all the future messages you'll send, and I'll also be able to tell all the previous messages you've sent. And then what I can do is have like a sort of a soft fork, and I'll just ignore your messages until I have a chance to stash you in the smart contract. And we could even go a step further and say that, okay, and then I would share those messages with everyone else. I would share with all my peers. I would say, oh, this user broke the rules. Here's their public key. Here's their private key. Don't listen to them. So we could kind of gossip it through the network, I suppose.
I have a small question and a bigger question. So the small question is just like a bit of a technicality, but what happens when somebody sends like the exact same message repeatedly in an epoch? Like, was it?
That's totally fine.
Okay, so you could send like the same message like 20 times, but it wouldn't reveal any new nullifier stuff, but people would just ignore it then? Like, would that not be its own weird vector?
Because we're doing this in a peer-to-peer network, you kind of assume you're going to receive the same message a number of times.
Got it. And then I guess bigger question is, how do you envision groups forming? I mean, it obviously depends on the situation, but like, yeah, you don't need very much stake to participate, but like, you could be in the group like 50 times if you have more stake, right? And I mean, that's part of how it should work, but I'm just curious if you could go into more detail for how it might be used in a particular situation.
Okay, yeah, so there's a few like applications that we could use this for. One application is to sort of as like a universal login that you can like log in a limited number of times. So the obvious kind of Web 2 application would be like VPN login. So you can anonymously log into different VPNs, and even the VPNs wouldn't know who logged into, how many different accounts you logged in from. So that's one use case, and then there's like sort of the status kind of use case where you have like Whisper with proof of stake, and you want to just send a bunch of messages. That's another use case that's interesting. So if people want to join the group more than one time, that's interesting question. So one thing we could do is if we implement the kind of payment mechanism, we could have a system where when more people join, more people are incentivized to participate and sort of transfer messages. That's one thing that we could do. Another thing, I suppose that you have to accept that. You have to accept people coming forward and saying, I want to join more than one time. And then the next question is, if we use it for ETH2, what if someone comes along and says, oh, I'm going to join 1 million times, and I'm going to stick to exactly the rate limiting, and I'm going to DOS the system that way. I'm going to put down $1 million, I'm going to have 1 million messages per second, I'm going to use that maliciously. So one thing we could do to sort of limit that is to burn a portion of the Ether that they deposit. And that would put like an economic cost on what they're doing. But it's still a vector, and I guess you have to include that in your kind of protocol assumptions, that you have a DOS attack and it costs this much money. And I guess that's the kind of difference between the previous mechanisms.
Well, in the current mechanism, you are very limited. In the current mechanism for like slashable stake mechanisms, you're rate limited to the messages that you can send because you can be slashed. But this potentially adds like a layer of privacy on top of it, which is definitely worth investigating. So just by posting a stake, like you have stake at risk, and you're limited to the amount of valid messages you can send per epoch. But now, if we add like a layer of privacy to it, it could be a net benefit. Does that make sense?
Kind of. I was more thinking about using it for like peer-to-peer rate limiting, and you're talking about using it for like proof of stake messages.
Right. Which for ETH2 are kind of one and the same.
Which for ETH2 are kind of the same thing, at least on the core protocol?
Yeah.
Yes, I see. Yeah, that makes sense. Okay, cool. I have like 2 more minutes if people have more questions. Also, if people would rather talk afterwards, I'll be here. We can chat about it. Any more questions? Oh.
Thank you, Barry. So I do have one small question, which is we can see various types of mixed networks coming out. And I think there are different ways to implementing anonymous network, either off-chain or on-chain. So on-chain, obviously you're using a proof of stake on-chain, right? Like so, we can have a sort of a smart contract, and it could actually be implemented on any blockchain. And I'm wondering, what's your opinion on those solutions that do anonymous network like off-chain? So is the anonymous network, is it possible to be integrated in the sort of basic networking module like the P2P, and what's your opinion on that? Would that be a good solution?
I'm not really too sure. I suppose I would have to talk to some of the P2P people and see what they're interested in. I think it's probably better to experiment with these mechanisms on layer 2 first, and to sort of try and see how it works, because if we fail on layer 2, that's not as catastrophic as failing on layer 1. Yeah.
Okay, thank you.
Okay. Okay. Yeah, thanks everybody. I'll be around. You can ask questions.
Let's give Barry a big hand.
Thank you.